Welcome everyone. Thank you for joining this session on offshore wind collision detection systems. My name is Jos Visser. I organized this session together with Angus Cook and Jesper Kiet Larsen, who are in the panel, so they will introduce themselves later during the panel session. I work at the Dutch government in the WOZE program. That is a government-led research program into the effects of offshore wind. And I personally work on birds, and of course also on collisions. Let me see. Yeah. So that song relates to the different aspects of this session. Then we go to the next slide, I guess. Yes. So what are the aims of this session? To showcase studies across the area of technologies and some of the data collected to date. Discuss general considerations for collecting evidence related to collisions and how to optimize its use in advancing and validating collision risk models we're using right now. And acknowledge the challenges, collecting these data and discussing the key priorities for overcoming these challenges. So how we will do this? We have different things. There will be several presentations showing the possibilities to measure collisions offshore, and a short presentation on the developer's perspective by Jesper. And this will be followed by a panel discussion on what we can do with the outcomes of all these offshore measurements. And there will also be some involvement of the audience, because we want to make it a little bit interactive and to get you a little bit active after lunch. So I have some questions for you. I think, yes, there's the first question. Stand up if you think we would still see collision risk as a big problem if we had camera systems available 20 years ago. And camera systems, of course, I mean high quality, technological good quality camera systems we have right now. If we had them already 20 years ago, would you think we would still see collision risk as a big problem or not? So if you think you would still see it as a problem, you can stand up. If you think we would have solved everything, you can sit down. And if you don't know it, just sit down. So I think that's like, well, I guess like 60, 70% is standing up. It's not really clear exactly how much it is. So now let's start with the first presentation. There will be room for questions after the three presentations. The first presentation will be by Mika Repas from Strix. Yes.
Do I see what's being presented in the back? Is it? Oh, there it is. Okay. Well, thank you very much. I'm Miguel Repas from Strix. I'm here to present on our seabird interaction studies at Nagoite offshore wind farm. I'm presenting a work that is really built on the shoulders of a very large and very diligent team from many different organizations, from Strix, from NINA, from the University of Lisbon, Core IT, and of course, the NNG team. I wish to thank also, the Nagoite offshore wind, and of course, the other Fortente developers, Seagreen and Berwick Bank, for supporting this study. So we know that seabirds represent a key consenting risk for offshore wind farms. It is crucial to quantify that risk, the risk that the wind farm may present to seabirds. It is crucial also to understand and identify the underlying mechanisms of behavioral response of birds to operating turbines, and reveal those species-specific factors that enhance avoidance and therefore affecting collision risk. Now, this study has been designed and uses a combination of AI-powered 3D radar and high-resolution video imaging to study seabird interactions with operating wind farms. A study of such scale and detail is a first in the UK, and I also wish to thank the advisory group, the first FTRAGO, for endorsing this study, some members of which are sitting in the panel here today. Thank you. Now, looking at the NNG offshore wind farm site, it's a site that is located just off the coast of Edinburgh. It's a 450 megawatt offshore wind farm in the Firth of Forth, or just outside the Firth of Forth. This wind farm has reached operation earlier this year, so we reached commercial operation date this summer, which is a major achievement for this project. It's a project, the study is focused on two key species, so the northern gannet and the black-legged kittiwake. It's a study that aims to look at the behavior of these birds around operating turbines during breeding and post-breeding seasons, and we are aiming to collect the data during the year 2026 and 2027. Right, so the study aims to address a few fundamental questions. We are a science-based company, and we have been challenged with addressing these very specific research questions, for which we prepared a robust study design to ensure the scientific delivery of the project. And the questions are really focused on collisions, on avoidance behavior at multiple scales. So the first question is really, do we have empirical evidence? Are there any ways of actually getting evidence of collisions occurring at offshore wind farms? And if so, if there are such collisions, what are their actual rates? The third question is focused on the reactive behavior around these turbines. Are there such reactive behaviors? And can we actually accurately record them and understand how close they occur to these turbines? At which distance does this behavior occur? And is it weather or site-specific? What other variates or covariates would explain and affect this avoidance behavior? Can we use this information to understand collision risk to seabirds? And does that collision risk and that behavior also change over time and seasons? So those are all the very specific questions that we will address on this study. One important note is that we've designed this, this study leveraging on technology. So there's a lot of different components of technology involved in this study. So we have a 3D radar coupled with long-range tracking video. So this is a radar-guided video camera that enables tracking birds at the distance and do simultaneous species identification. The main components of the system, of course, are a primary radar as a primary sensor under which different slave systems operate. The secondary system is another radar operating on the X-band, operating vertically to acquire altitude, enabling 3D data and positioning of the bird targets. And of course, by tracking these birds in space, in 3D, we can inform the tracking system and the video system where to point and zoom in and record a video snippet, allowing for species identification. We've placed those systems very carefully in the wind farm site. So there are 3 points where we have such systems. One is really inside the wind farm, inside the footprint of the wind farm, and 2 in the vicinity on the outer edge of the wind farm. The coverage of these systems has been designed to also not only allow for tracking birds inside a wind farm, but also around the wind farm. And particularly, we want to look at certain effects like edge effects, like what is happening in the borders, in the borderlines of the of the wind farm, and looking at also certain corner effects, certain particular parts of the wind farm. Oops. Right, so this is how it looks like. There's been significant planning into this. It's now deployed at the site. The collision detection system is a different system. It's a fully video-based system. It consists of a ring of cameras placed in the bottom of the turbine looking upwards at the rotor swept volume, enabling a full coverage of this rotor swept volume, plus an additional 10-meter buffer around this volume. And you can see here the plans and the design. The cameras are mounted on the rails of the platform. So there's been extensive planning. This is where we are at this time. We have reached commercial operation date. The wind farm is installed and operational, and the study is about to start. Just a slightly more detail, we are now moving on in the next few weeks into a dry run of the systems. And starting spring next year, in March, we will start the actual acquisition of the data during the operation of the wind farm. We will have boat surveys as well as the technology-based data set. So I think I'm going to overrun a little bit of my time, but if you allow me for an extra minute. So this is we aim to estimate the collision risks. So this is the AI-based video system that allows, it's got object recognition as well as species recognition embedded. We will use advanced statistical tools to address the influence of variables on this collision rate. And in particular, we do expect a zero-inflated kind of distribution on our data set, so specific and very cared statistical tools are considered. We are looking at micro-avoidance within the rotor swept volume by looking at those video snippets and measuring changes in flight behavior of these birds. We'll also be looking at meso-avoidance, looking at flight trajectories of birds that successfully navigate between the turbines. And so we'll be looking at using different types of approaches. One is based on differences in densities, the other one on analyzing individual trajectories. Yeah, very quickly, and then macro-avoidance as well. So we will have different approaches for estimating all those different things. So in conclusion, thanks. There's been so much planning and engineering, and I want to acknowledge first all the efforts under a very challenging and changing program implementation. We're almost there. The technology is there. The wind farm is there, so next season we will have results. So we're really, really looking forward to the next steps, and we will be seeing those results, those much-awaited results very soon. So thank you very much, and thank you for your patience. Thank you.
Yeah, you can see. So thank you, Miguel. So, well, it's quite clear, Miguel has a lot to tell. So if you have more questions or things, you can ask Miguel. Now you go to the second presentation. That's by Mamouna Birges Shami from Spoor.
Thank you. Hi, everyone. My name is Mamouna Birges Shami. I'm a software engineer at Spoor. My background is in computer vision and AI, so I can't really name this bird species, but I can train models to do that. I'm here to present the advantages of stereo vision for collision detection offshore. Yeah. I don't think I have to make a case for why accurate collision monitoring matters, because we have seen, like in the workshops yesterday and today in the morning session as well, everybody agrees that we need to move from modeling towards measuring and gathering data of collision offshore. Just to put it a little bit into perspective, we have around more than 600,000 turbines installed offshore and onshore combined globally right now. And the number is projected to be more than 800,000 by 2030. So even if it's a single collision, even if it's really rare, it's a single collision at a turbine and like 6 months, let's say, the cumulative effect is extremely great, and it affects the species behavior, habitat, etc. So it's extremely important to monitor collisions. The challenges we have offshore are many and a little bit different than onshore. First of all, since collisions are extremely rare, it's really easy to miss a collision. And then carcass retrieval is not feasible offshore. Even if you were to do carcass retrieval, not all collisions result in imminent fatality. And then you're missing the context if the bird was just tired and resting on the platform, or was it actually a collision or not. So we did a project at Aberdeen with Vattenfall. Aberdeen is a really interesting site because on the coastal cliffs you have the colonies for kittiwakes. So we did a prior project with Vattenfall where BTO validated our system. SPU does bird monitoring with camera-based bird monitoring with monovision, and then we had an experimental stereo vision setup at this site, and BTO validated our monovision and stereo vision method for this. And then later on, we did the collision monitoring at the same turbine using the same setup for 18 months. And this is the site where we did the project. The turbine encircled in yellow is where the camera was installed. The stereo system was installed, and I was looking towards AWF05 turbine. The distance of this turbine was 881 meters, so it's pretty far away from the camera. The system we had was, so initially we had planned a 12-meter baseline, so the distance between two cameras, that's what baseline is. We had planned a 12-meter baseline, but we realized it was not feasible to install such a long railing on a single turbine, so we had to reduce the baseline to 4 meters. But we have a poster for the results of this study if somebody's interested in looking at the results. But here, just a short summarized version from the BTO study where they validated the tracks. You see, these are tracks from 3 birds. So each picture is like a bird track, and it's reconstructed using mono and stereo data. And the green band you see, that's the laser rangefinder data. So the red tracks are the mono reconstructed, this study concluded that our mono system overestimates by 50% consistently, and stereo underestimates by 20% consistently. The study also concluded that the range for stereo was around 500 meters, but we see from 400 meters onward, the tracks look really squiggly. A little bit unnatural for the birds to fly like this, unless they do, but they're so squiggly. So the uncertainty was really high after 400 meters because of the short baseline. The range was limited for stereo. So when we wanted to do collision monitoring, what do we use? Do we use stereo or do we use mono? Both methods have their own pros and cons. With stereo methods, we have great accuracy. The accuracy is higher than mono, but the range was limited, so we couldn't use it for collision monitoring. And then for mono, we had the long range. We could detect birds at turbine level distances, which we needed, but our accuracy was limited, so we couldn't use it for collision monitoring. So then what do we do when we want to monitor collisions? We had a lot of videos. We had more than 7,000 hours worth of video, and then we needed some manual intervention for this. So the method that we ended up using for collision monitoring was that we use our SPUR's algorithm to detect all bird-like objects at this site, and then we define a turbine vicinity box, the rectangle box you see here. We define it in the camera view, and if you extend this in a 3D space, you project this turbine vicinity box in a 3D space, it consists of a large volume. This volume is extremely huge, and we had to look at all the birds entering or crossing this turbine vicinity volume. Some results, just to focus on something that our algorithm detected 190,000 bird-like objects, 133,000 were actual birds, and 115,000 crossed the turbine vicinity, which we had to monitor manually. We found 6 possible collisions and 2,500 interactions. And our ornithologists looked at all these possible collisions to see if they were actually collisions or not, but they were not. This was an example of an interaction, really interesting. The bird was soaring in front of the rotor hub, and it waits for the turbine to pass, and then it just flies under the turbine blade, which I just think is a really interesting interaction. This was an example we had of a possible collision. Is it a collision or not? Okay, so this is obviously not a collision. The bird is really large, so we know that this is really close to the camera. It's not at turbine level distance, but just to mention, this track, the track you see highlighted in red dots, this is what we would expect a collision to look like. The bird is flying, and then it just falls straight down. But this is just bird is diving for food. We had another possible collision here. The bird you see is really small. That means it's really far away, and we calculated the distance. It is at the turbine level distance, so it could have been a collision. Okay, I don't know if it was clear on the large screen, but it actually falls down. So then, since we detect in front of the sky background and we mask the other background, so then we went back and manually labeled the part where our algorithm stopped tracking it. And we see that the bird flies around and it lands on the railing. And then after a few minutes, it actually flies away. So our ornithologist concluded this was not a collision. But just this led us to believe that we can detect birds at the turbine level, like it was landing or sitting on the turbine railing, so we had a pretty good detection range. The lessons we learned through this were that, first of all, we needed a large manual effort to look at the birds through the risk zone, so we need something to reduce this manual effort required. And then stereo is, of course, better than mono, but we need a large baseline, which is not feasible at a single turbine. So using the lessons we learned from this study, Spoor has this ultra-wide double viewpoint setup we installed on some sites now, and we see some early results. But the setup is such that you have 2 cameras installed in perpendicular to each other on 2 different turbines, looking at the turbine of interest. And if you look at the observation volume, it reduces quite a bit from like that long cone to this 3D cube just around the turbine. So our main goal was to reduce the amount of manual effort we need. This is one of the videos that we've seen so far. It's like really early. We are processing the results, but as you see here, the bird, this is the same turbine in view from both the cameras, and we are able to triangulate the position of this bird. It's at the closest point, it's at 38 meters from the blade tip. And our margin of error in this is 10 meters, less than that even, but just this makes it possible to do collision monitoring offshore. Thank you so much.
Well, thank you, Mamua. Also some nice videos, and I hope we also have some nice videos in the last presentation. This is by Femke Warmer from Wageningen Environmental Research.
Yeah, so thank you. I'm Femke Warmer from Wageningen Environmental Research, an animal ecologist and researcher. And I will be presenting today also on behalf of Karen Krijgsveld, the project into measuring bird and bat collisions at an offshore wind turbine. And of course, we know that millions of songbirds migrate across the North Sea, and they do this mostly at night. And this makes them notoriously difficult to detect, let alone see a collision. So there is quite a concern for songbird collision at night, and expectation can vary tremendously on how many collisions there are. Do calculations from onshore turbines relate to offshore turbines? Are songbirds different from seabirds? That are all questions that influence what we may expect. But we know that there is a potential for collisions. We just need to gain insight. And this is where our pilot study comes in. It's a trial into a new technology for offshore collision monitoring. And it's a collaboration between Wageningen University and Research, Vattenfall, and Wildlife Imaging Systems. And it consists of thermal cameras that can also detect falling objects at night. And it's supplemented with acoustic monitoring. And we are monitoring during spring and autumn migration of this year, so we're still in the middle of our project. And we are monitoring at a single turbine off the Dutch coast. So the main system consists of the WIS thermal camera monitoring, and we have two sets of cameras. We have a set of camera that is looking out horizontally across the sea that will detect falling objects that could possibly be collisions. And then we have also a set of cameras that are looking up along the turbine to monitor the activity in the rotor swept area. And in addition to this, we have an acoustic monitoring setup, as I mentioned, and this is just to provide additional information for context. And we have bed call detectors on the transition platform, and we have bed and bird detectors on the nacelle. And the WIS team also has the video processing setup of the thermal cameras. And the 5-minute recordings are turned into summary images, as you see on the screen. And then their models can generate tracks from those images, and can classify them into different groups of bird beds, insects, and planes. And there's also a model to detect falling objects. So the vertical tracks that indicate that an object is falling. Hopefully, it could also be an insect flying through, but that's what we are working on. And they have a poster for more information. So then we have the system in action. We are still in the middle of our process, but we have some initial collisions possibly that we see. And I want to show this first example. So on the image on the left here, we see a vertical line going down, a faint line next to it, maybe not visible for you, I don't know. And this indicates a falling object. So then we go search further. Is this a collision? And then we look at the vertical cameras looking up to get the context of what is happening around the rotors. And then we get this video from the vertical cameras, so it should work. Yeah. Here we see an animal, probably a songbird, entering the frame, struggling in strong winds, also swept about by the rotor. It's struggling clearly, and then it gets hit. So that's quite a good confirmation that this is actually a collision. So these are the horizontal and vertical at the same time. So yeah, it's quite a clear graphic example of what is happening, and we are still working on if we get more of this, but yeah, it's a very good confirmation. And the summary image of the video I just showed looks like this. So there's also lots of parts falling down. And that is also visible on the image here on the right. It's another night in March where we see another cluster of falling objects on our horizontal cameras that are behaving similar to the summary image of the video I showed before. So this clearly shows our system is working. We are detecting collisions. We are still in the middle, as I mentioned. We are working on data analysis and interpreting the context. So using all the channels we have to understand what is happening. So we are working on reviewing the footage at the moment, optimizing the models for the auto migration that is coming. And we have currently done filtering of the data and come up with a possible 500 collisions. That's a lot. Possibly a lot of false positives because we are including everything that has a vertical track. So there could be an insect flying from top to bottom, it could be a falling object, it could be a collision. So we are manually reviewing this footage to validate what is happening and to train our model for the coming migration season. And the main challenge we have at the moment is interpreting the context of these vertical tracks. What is happening? And for this, we can look into flight intensities and we can look into species present. And the graph here on the screen is flight intensities from two monitoring systems. One in the orange dots is the radar, the bird radar that is at the wind farm that our turbine is located. And in the blue is the flight intensities that are calculated from our upward-looking cameras. And it's very nice to see that they overlap very nicely, showing peak nights during spring migration in the first part of the graph, and then lower flight intensities later into the season. And we can use this also to understand if collisions are happening during peak nights of migration, if they are happening on low intensity nights. So we correlate this with possible collisions that we see. And then we also look at the presence of certain species, and this is where acoustic data comes in. We use this to understand what is happening. We hopefully also collect some bird data and bed data from the nacelle, but shown here on the screen is the bed detection from the transition platform. And we have already shown that there are 3 different species visiting the turbine during April and May this year. So we have a Nethusius pipistrelle, a common pipistrelle, and an Aptescus nestalis species that was probably a common noctule. And they've all visited the turbine, and these acoustic echolocation images are from the recordings from the turbine. So it's really nice to see that there are at least already 3 species visiting the turbine. So that leads us to the summary of where we are at the moment. The system has shown us 2 collisions already, and this is just after 1 migration season, and that was the spring season, and we are expecting possibly more collisions during the autumn migration as there's higher volume of birds coming through. And we haven't done a thorough analysis of the data. We are still working on that at the moment, so this is just a start. And that also leads us to that it's too early to tell how many collisions we will actually get to see and how accurate they will be, because anything can fall. So we are working on validating using the vertical cameras, the acoustics, flight intensities, all that, and that takes time. But we've shown already here today that we have made a big step forward because we can see collisions of songbirds at night using these thermal cameras offshore. So that's very interesting. And if you want any more information about the technical side of things, WIS, Wildlife Imaging Systems, has a poster today on the topic of their development, and our project team is present today as well. So thank you very much.
Well, thank you, Femke, for your presentation. Now I would like all the presenters to come onto the stage, because we now have 10 minutes room for questions. So has anybody a question to one of the presenters? Please raise your hand.
Hello, thank you for presentations. I'm Julius Morkūnas from Lithuania Consultancy. I'm wondering how many of these systems you have to install in the wind farm to have the number of estimation of the total collision. It should be each VTG equipped or a certain number or percentage?
Which system are you talking about? Like the camera system? Any system?
Any systems. 3 of you can answer any.
I can't speak for the other systems, but for camera-based, it depends how much coverage do you want for. Do you want just the parameter coverage or like inside the wind farm? Depends on the camera resolution. Like a lot of different factors go into it. It's not a simple answer like 10 cameras are going to cover everything. But we do know that if you, for our stereo vision setup that we have right now, you will have to have 2 cameras at like turbines perpendicular to each other looking at the turbine of interest. So I am not sure what to say. I don't have an exact number for you, sorry, but maybe.
Yeah, at the moment we are just researching for our part at 1 turbine, and the system of the study is continuing to a different study looking at more thermal camera setups. And we are still at the moment working on the pilot of is this technology actually working offshore? What can we see? So I think at the moment it's very difficult to say how many systems you would need to install to get full coverage or to put it in practice, I think, if that answers your question somewhat, yeah.
Miguel, do you also want to?
Yeah, I think I agree with everything that has been said. It's not a very easy calculation. There are so many factors to consider. Of course, it really depends on the purpose, first of all. So, indeed, do we need full coverage, or do we need to provide coverage for selected turbines? for each turbine, what is the volume that you want to get covered? It really depends also whether that volume is being covered by nearby wide-angle kind of cameras or long-distance, zooming in, very narrow lens kind of cameras. So that all those different things factor in. Each will have its own advantages and challenges. So it's not an easy, straightforward answer to your question.
Oh, thank you. Is there somebody else who has a question? Okay. Yes. Oh. You'll be next.
Rob Simmons from South Africa. A question for Femke, please. You said with your bird and bat detection system, you expected a 90% false positives. Why so high?
Yeah, that's based on the filtering that we did. So the filtering to get to these possible 500, that was also included tracks that were marked as insects or other objects. And the camera's vertical track can also mean an object flying away from the camera, and then it looks like a vertical track, but when we look at the actual recording, it's just flying away. Insects pass through the frame that can fly from top to bottom, or from bottom up, and then it's not falling, it's going up. So it's really a very rough filtering to allow for this manually review of the footage, to label and train the model. So it's on purpose that we have a lot, and therefore we know that it's a lot of false positives, but that's built into the filtering, yeah.
Thank you. While I have the microphone, second question, very bad, I know. Are any of you now going to go one step further and do a shutdown on demand once your cameras have detected a bird or a bat at night?
I think that's actually more into mitigation, so that's not really a topic, but maybe you can answer it if you...
I'm not really sure on the next step. Maybe a colleague of or one of the project team knows that, or maybe for your projects you can answer.
I can answer for Spore. It's in the roadmap. Our first goal was to accurately localize the bird. If you know the position of the bird really well, like you know it's flying close to the turbine, then of course you can do so. Of course, curtailment is in our roadmap, but we don't do it currently. That is the next step.
Yeah, that's a really interesting question. With respect to our work, of course, we do work with video systems as well as other types of sensors, including radar and acoustics. And we've been doing radar-assisted shutdown on demand for many years. We actually pioneered the methodology, so it's been around for more than 15 years. So yes, it's there, it exists, it's readily available, and it should be implemented widely.
Thank you. I think the woman over there had a question. Yes.
Hi, Shiloh Felton from Renewable Energy Wildlife Institute. I also am going to be bad and ask two questions. So I apologize. One, for the Spore stereo vision, I was wondering where the cameras were, and I'm sorry if I missed that in the presentation.
For Aberdeen, cameras were installed at the base of the turbine that was looking towards the turbine of interest.
So it was the ones that showed the full turbine were on the base of the turbine?
On the other turbine, like I showed in the project site, but there was one turbine. Imagine this is a turbine.
Yeah.
The cameras were here, and they were looking towards the turbine of interest. So it was the turbine of interest was 800 meters away from that turbine.
And then my second question was asking you guys if you know if there's any appetite for this kind of remote monitoring onshore to replace, dog teams and other such things for small animals.
We have similar setups onshore as well for collision monitoring. Yeah.
Thank you. We have, I think, room for one or two more questions.
Hi, Ulrike Drijssen from Waardenburg Ecology. I'm wondering for the cameras, some of them are very far away and some are pretty close up. And the imagery you showed seemed pretty detailed, but is there any chance that you can do species recognition from those images?
Is this for cameras looking from far away or like cameras looking up? I feel like I'm talking a lot. I can say, I guess, in our system, in the videos that I showed, the last video where you see the stereo vision setup, and you see a zoomed-in crop of the bird. So if the resolution of the camera is good enough, you can do species ID looking far away, but you have, obviously depends on the bird size, like which species it is. It's a pixel per meter resolution, how far you can do species ID. Alternate is you have a PTZ camera where you zoom in, you detect the bird in the overview camera, and then you zoom into the bird, so then you can do species ID much better.
Sorry. So that's not part of your project at this point to do the recognition?
We currently do species ID, but most of it is manual species ID. We do train AI models, part of it, but we realize that it's not that good enough. We don't have a good enough resolution from cameras looking far away. So now we are doing a PTZ-based species ID. That's in the roadmap.
Yeah, I'll just to speak on behalf of our systems, we do also object detection and species ID on both the systems, the close range as well as the long range, so long as these species are within the operational range of the system.
Okay, thank you. One very small last question. Anybody has a question? A small one.
Hi, Constance Blary, Senior S France. I have a question for the three of you. You all talk about collisions, but what about birds that didn't collide but will die or suffer from the passage, like barotrauma? Are you able to detect the trajectory if it's different, or to detect far enough the bird?
So if I'm correctly understanding your question, it's not the collision that's the problem, but it's more like a barotrauma, and you want to see what happens after?
Because
passage?
those birds will die too.
Yeah.
And I would like to know if it's possible to detect them or not with your system.
So maybe it's a question, it's better for you have an answer?
Should I?
Yeah.
Yeah, so we believe that with the camera-based system, you can actually find the collision, right? Like when the bird collides, even if it's not fatal. That's what we argue, that with carcass retrieval, you know the bird is dead, but you don't know, you're missing the context. So when you are looking from far away, and we are able to track the birds from far away, the bird I showed in like this revision setup, that's 1 kilometer from the camera, so it's pretty far away. And if you can track, you can see the trajectory, of course. But it's going to go as far as where like the camera can, like the extent of the camera view, but not further than that.
So thank you. I think we have to go to the next presentation due to the time constraints. I think if you have some more other questions to the presenters, which you probably have, you can ask them later after the session. So thanks again to the presenters. And now Jesper will give a short presentation on the developer's perspective.
Good afternoon. Yes, so I'm going to talk a little bit about our experience hosting radar and camera-based studies on bird collision and bird avoidance in our offshore wind farms, which we've been doing now for 10 years and across 5 different wind farms to date. That worked. Yeah, so here I've listed some of the things to consider, which might easily be underestimated. I won't go through them in detail, really, because it will just take up all my time, I think. But if you are interested to hear more about some of them, do reach out to me, and maybe there'll be time for a question on it, but in any case, just reach out to me afterwards, and I'm happy to share some of our hard-learned lessons about going about this. I'll just give you the very short version of it, which is it's difficult, it takes time, it's costly, but it's also feasible. If that is, it's approached with respect for the wind farm and its operation and the environment out there, which is not a small thing. It's a bit of a task, I can say, to manage such studies, and has earned me a few gray hairs. And someone recently suggested, why don't we just train some belugas to find these birds out there, sort of a kind of nature-based solution to collision monitoring. And I must say, I'm a bit tempted by that. But that's something to get back to, maybe, at another conference. When we do it, we should make sure it's worth the effort, that it moves us forward. And I think there's at least these sort of two elements to that. One being understanding the data we are collecting, and the other one being efficient about it. Let's see if I get it on. And talking about camera and AI-based technologies or any other new technology for that sake, it's crucial, I think, that we bring all parties along, that we take some very careful first steps and that we do it together. I'm a big believer in trials with independent expert scrutiny and with the key stakeholders closely involved, which is the approach we have attempted in our study at Aberdeen with the SPORE system, and our study now ongoing at our Dutch wind farm, Hollandse Kust South, with the wildlife imaging system, camera system, where we saw, we saw two presentations originating for those studies. Yes, that, and of course, which is really essential as well, I think, that the providers of these solutions are willing to let us into the machine room so we can see sort of inside the box. Because to be able to build confidence in these kind of data, which is a new kind of data, we need to be able to see through what we are presented with, and hopefully influence a bit the design of these systems so we can sort of deliver the kind of data that we need and can use. Yes. There's lots of obstacles out there. What you see on the left is sort of 5-minute summary image from one of our thermal cameras at HKZ, like the ones you Femke showed before. I think it's quite a piece of art, actually. But can you guess what it is? What's going on in this picture? It's a horizontal-looking thermal camera. No, it's not. No? Even the birds get in the way out there. Yeah, that's actually me. I'll leave it with that.
So thank you, Jesper. I think you can go back up, because now we'll start with the panel discussion. So I'd like all the members of the panel to come. So during the panel discussion, I will also ask some questions to the audience, so don't fall asleep. I have to find a nice place to sit. So first I would like to let the members of the panel introduce themselves. I think Jesper already introduced himself. So next I think is from the NGO Ellie McCloskey.
Thank you. Hello everyone. I'm Ali McCluskey, Principal Conservation Scientist in the RSPB. My job is kind of threefold in an ascending order of pleasure. I kind of review the offshore wind assessments for the RSPB and look at them, get involved in the scoping stage and make decisions about whether we object or not. I also manage a research programme throughout the UK waters, largely tracking seabirds. And finally, I get involved in projects like we've just heard about and offer advice and get ignored.
Well, thank you. Next on the regulator, Erica Nutt.
Hello everyone, how to follow Ali? Well, I'm Head of Marine Energy in Nature Scot, which is a statutory advisor to Scottish Government. And for my sins, I was involved very early on in both the Spur project and the Strix project that we heard about earlier. So I'm here to answer questions not from an ecology point of view, because I'm not an ecologist, hence my suggestion about the beluga whales maybe picking up dead birds, but yeah, I will pass on to Angus. I'm just here as kind of wallpaper, I think.
I'm Angus Cook. I'm a senior principal consultant at the Biodiversity Consultancy, and I've been working on collision risk and modelling and stuff for I mean, my hair was much shorter than this when I started. But yeah, I've been involved with projects with Jesper and Vattenfall for a while, and yeah, so I've done a lot of stuff on collisions. So I'm sort of trying to provide a bit of a science perspective.
Yeah, thank you. So we have people from all different backgrounds in the panel. So I'd like to ask the first question to Jesper. What do you think are the key risks and costs to developers from these types of studies?
Yeah. I think on this thing about, I think there are obviously risks, but I mean they can all be sort of addressed and mitigated to a large degree, I think, and there's cost. But I think sort of really sort of the main challenge for us is sort of this interface between the studies and then sort of implementing them in the wind farm context, because there's a lot of, it's not a simple task. Of course, it's a power plant and on being operated under some quite different conditions, being offshore, so there's a lot of procedures, and there's a lot of people that need to be involved to figure out whether this great solution of sticking some things, additional things on the turbines can work out, or if it's any threat or any risk in any way to the operation of the site. But it's all something that can be, I mean, we can work that out. Usually, it just takes time, and it's something that it's hard to plan really in detail, because it will be subject to things happening, yeah, from the weather to major things on the wind farm that needs to happen, and this unfortunately will come a bit, or by necessity will come a bit sort of second, often getting to install equipment or sort of service equipment. So it's a matter of fitting that in. So it is a bit of a difficult environment, sort of implementing it.
Yes, thank you. I think we now can have the slide up. Does everybody see it? Okay. So because the answer of yes strongly relates to the first question to the audience. So please stand up if you have tried to measure collisions offshore. So let's see. Actually, well, there are quite some people, I think. but who of you actually, you can stay standing if you have seen a collision?
Should we caveat that, have we seen a collision offshore before this afternoon?
Yeah. Oh, there's still some people, but not a lot, I think. Because, yeah, I think we are talking a lot about collision. Oh, thank you. You can sit down. I think, or you can keep standing. Oh, yeah. Yeah, we can. Yeah, maybe we can ask one question to someone of the audience who actually did see a collision. Maybe somebody can tell something about it. If somebody wants to.
Hi, I'm Arnoud from Spoor. So, first thing, when we see collisions, we're unfortunately not allowed to share them often, but I can tell something about it. We saw a very interesting collision on one of our offshore projects, where the bird actually collided quite hard and was heavily affected, went down, but it recovered and it flew away again. So, something very interesting also to think about when we talk about collisions. Are we only interested in the fatal ones, or are we also interested in the ones that are not immediately fatal?
Well, probably you have to follow them then longer to see what happens days after. So maybe, thank you for that answer. Maybe to the panel, because we're talking a lot about collisions, but yeah, not a lot of people have actually seen them. So maybe it's not that big of a risk. But question to Ellie and Erica, what would be an acceptable level of risk?
I think I got the short straw to start this one. Acceptable level of risk. I think that's very dependent on what the project is and where it is. So you've heard about two different ones in Scottish waters. One's very close to shore and close just really to Kittiwake. Another one is slap bang, very close to a number of seabird breeding colonies. And I think we've approached each quite differently, and it's been down to the questions that we've been trying to answer. So I think the level of risk is very much dependent on the project you've got. And there was a question earlier to the panel about shutdown. I wanted to address that because particularly in Scotland, we're dealing with multitudes of seabird flights per day, per evening, per night. And so shutdown isn't really an option for seabirds. It might be for other species, but I wouldn't say it is for seabirds. Probably not acceptable from a financial point of view for the developer, or from a regulatory point of view in terms of compliance and how do you monitor that. So, Ali, you got any more thoughts?
Yeah, the short answer is I agree with Erica. It depends. It depends, and I use that to caution against the idea that there are thresholds off the peg available to make these kind of decisions. Such thresholds are essentially biologically meaningless, because you need to look at these predicted impacts in context, and there's a lot of context you need to look at. You need to look at things like local, biogeographical, and national population trajectory and productivity. Things like that. You need to look at it in the context of catastrophic effects. We're all aware of what's happened with avian influenza and what may have been an acceptable level of risk 5 or 6 years ago may not be anymore. So it very much depends. But ultimately, I think the decisions about the acceptability of risk are a societal decision and not one necessarily to be made by scientists. The sort of studies that we've talked about here, what we aim to get out of them is to be able to improve our predictive ability, and through that to have confidence that our predictions are indicative of the scale of risk. And from that, and having confidence in that, it's ultimately a societal decision whether that's acceptable. And just finally, on that kind of, sorry, I said it was going to be a short answer. On that confidence, one of the confidence in the predictions and confidence in these techniques. All three of the projects that we've talked about, that gave presentations today, all have gone through really thorough, Jesper talked about this, about really thorough validation, bringing in all the stakeholders to see that and have been really transparent. Miguel didn't get an opportunity to talk about it so much with SPUR, but the SPUR system has had a really thorough validation and understanding of the inherent biases. Every system of measurement has bias, and the way to deal with that is with honesty and understanding it. And that ultimately improves our confidence in the predictions that these systems feed into, and with that confidence, it's much easier to make decisions on the acceptability of risk.
So thank you. So I think we need high quality studies, but also, of course, a lot of studies. More studies would help. So that kind of leads us to the next question for the audience. If you can get the next slide, please. Oh, I can do it myself, I think. That works. So, question to the audience. So everybody can stand up, please. So first of all, stand up. And then the question is, how many studies do we need to be confident about the extent of collision risk associated with offshore wind farms? So I will give numbers, and if you think, well, that's enough, then you can sit down again, or if you're really tired, of course. So 1 study, 5 studies. Oh, I see already somebody sitting. 10 studies. 25? 50? No, a lot of people think half the room thinks 50. Well, we're there. Okay. 75? 100? More than 100? Okay, well, thank you.
It depends.
Yeah. Of course, it depends on the quality of the studies, but I think it's interesting to see that some people already think 10 studies are enough, and other ones think not more than 100. But the panel, can you reflect on your own answer? And what other considerations to be taken into account? Well, I think Ed already gave an answer, but maybe Angus?
I think it's quite hard to put a number on it, because I think there's quite a lot of inherent variability between the different sites, between the different wind farms. There's a lot of different things that are going to affect the collision risk. So it's, at the minute, I don't think we have quite enough understanding of how transferable the results from one wind farm are to another. So I think because of that, it's really difficult to say, okay, once we've done 5 studies, 10 studies, 20 studies, that's it. We've not got anything else to learn about collision risks. So I think we need to sort of get a better handle on that inherent variability before we can be sort of confident about what the true extent of risk might be.
I'll maybe just add to that. So one of the reasons we've had studies in Scotland is because we were looking around the world to find out who was doing what where, and we knew that the environmental impact assessments were all based on predictive models, but nobody could tell us how accurate or inaccurate these predictive models were, and there weren't so many countries that were developing wind farms quite so close to designated seabird colonies. That's another reason that I think we need to think about marine spatial planning a bit better. But the whole point is we didn't have anything to really accurately identify how close these predictions were. So we spoke to the developers, we asked them, how keen are you going forward to try and make it easier for the next developments coming along to make these predictions seem more accurate or not? So it's really good that we're having conferences like these to actually tell people about what studies are going on where, and to start us all thinking, well, how extrapolable will the results be from these projects? And can we start to think about, does that lower the number of projects, questions? Is it 100? Is it 25? Is it 1? You know, we're going to have to get there at some point, because the developers don't have deep pockets anymore.
Thank you. So, and do we need, because there are a lot of different people or organizations working, doing studies, so do you think we need kind of a set of standards for studies or analysis, so people do all the same? Maybe Erica or Jesper?
standards make me, is that working? Yeah, standards make me shiver a little bit. I think standards are good, but I think it's the basis for having those standards that need to be really carefully thought through. There's no point having a standard for the sake of a standard if we haven't really identified the question that we're trying to answer by having the standard. So, comme c'est, comme ça, wrong language, but there we go.
Jesper?
Yeah, that could have been my answer, I guess. Just to try and add a bit to that, I think, yeah, ideally, I think we are at a stage where we are first of all trying to understand what these technologies can do for us, and so I think we need to get that understood first, and then we will see, we will learn in the process something about collisions, and we will be in a much better place to see, to take decisions on how to sort of roll that out, and also to have a discussion about sort of what can we actually achieve, what is it, what is the level, what is the need, what is the level of precision or knowledge we are sort of aiming for, what is good enough, and so whether we need to do it for 100 years or maybe we can do it for a couple of years, really intensive, and get to the scale of it, and then we are in a good place maybe.
Angus, do you want to?
Can I just make a point there about standards? One of the things that introducing standards would help with is, at the moment, a lot of these studies are really facilitated by one or two individuals within the developer community that have a degree of vision and commitment and bloody mindedness to make them happen. So I'm thinking about dear old Jesper here. I'm thinking of Polly Tarrant, who's frowning at me desperately in the audience. But they need to have, they have had to push back both internally and externally to get these studies, to get the degree of rigor built into these studies, and to get the studies where they are past all the difficulties with insurance and installation. What standards would do would take the pressure off individuals like that and standardize practice across the industry.
I mean, I think there probably are some sort of general rules and standards that we could think about. I think I understand why Erica shivers, because it's sort of, if you start introducing standards and everyone tries to meet those standards, and maybe there's less innovation in a space that's actually rapidly developing. But I think at the same time we can agree on some basic standards, like if you're doing this study, as Jesper said, they're expensive, but the sort of collaboration is really vital, and there should be some standards around things like making sure the data is available, making sure that people can look at it and access it, understand how the systems work, and make sure that the data is actually used to improve our understanding about collision risk.
Thank you, Angus. That strongly leads us directly to the next question to the audience. So stand up if you think that we're making enough use of the data that we already collected so far. Well, nobody eager to stand up? Or maybe it's difficult. Maybe Angus, you already said something about it.
Yeah, I mean, I think there's a challenge. I mean, I think there's always more that you can do with the data. I think Miguel's study was really interesting, but he was sort of highlighting that they're focusing on 2 or 3 species, but actually, though, at the same time, there will be a lot of data that's getting collected that won't be analysed, and that just reflects the reality of these studies. It's really hard to get them off the ground. There's only so much time and effort you can devote to them, but I think that there's the potential to sort of maybe delve into the data in a little more detail, but obviously that requires more time, more money, more support, and that sort of thing. So yeah, I mean, I think there's definitely the potential to make much better use of it by sort of looking at all of the data that gets collected in a bit more detail.
Thank you. Somebody else from the panel wants to reflect?
Well, I don't like standards, but I do like principles. And I think there are some principles about where data is being collected, the availability and transparency of it for others who may not be involved directly in the project, but can make use of the data, as Angus is saying. You know, there's an awful lot of data out there, an awful lot of gigawatts or megawatts being used to store that data, and we're not making enough use of it.
I agree with Erica. Yeah, this works on various levels as well. It's not just the very complicated data sets that these sort of projects are generating, which frankly we need more analytical capacity within the community to deal with. And we've got brilliant modelers. We've got loads of brilliant modelers now, including in this audience, but we need even more to just deal with this volume of data, which is a great thing. The other issue with data is just accessibility, and that cuts across right from the survey data, from the sort of tracking data that we're involved in, just making sure that there is a smoother way to facilitate the sharing of that in a way that doesn't compromise existing studies is something that's really challenging for a lot of people, and it would be nice for someone to take the initiative to sort that out. Erica?
Not my pay grade.
Yes, so thank you. I think next question, I think that's also a really important one, because currently, of course, all using collision risk models to assess the number of collisions, but now we're going to start actually monitor collisions offshore. So how can we optimize the outcomes in these studies in advancing and validating current used collision risk models?
I think there's a few things we can be doing. So I think basically, and we talked about this in our workshop yesterday, you can break collision models down into different elements. And I think rather than trying to sort of understand if the number that gets spat out at the end is right or not, you could start thinking about, well, what about the different elements? How right or wrong are our estimates of exposure? How right or wrong are our estimates of the probability of a bird passing through a turbine, as we saw in Femke's video, and getting clobbered by the blades? What can we start thinking about how to use the data that we're collecting in order to validate those elements of the model, and then say, okay, well, which of these bits are working pretty well, which of them are not working quite so well, and how can we use that information to improve the models and assessments that go into planning for offshore wind farms?
Thank you. Anybody else for the panel? No experts on collision risks models. Well, now we go to the next question for the audience, and it is the same one as it starts. So stand up if you think we would still see collision risk as a big problem if we had these camera systems available 20 years ago. So I'd like to see if you changed your mind. So. So I think that's again about 70%. So maybe I can ask a question differently. Who changed his mind? Oh, not a lot of people. So okay, I think, well, like one person. Well, to wrap up, I have the last question to the panel. So if we were to start again, what would be the one key lesson we have learned so far in all these collision risk studies? The question is, if we were to start again, what is the one key lesson we have learned so far from doing what you did the last couple of years?
That we have started a bit earlier, maybe. Yeah. Yeah, I think it's what works really well is when we sort of work together on this, and we have done that, and that has been a great pleasure. But I think we can do that much more, and there's still room to do more along that in that setup. Yeah, we should just get on with it. It's a lot of fun, also, actually, and dealing with these guys, and they can be quite friendly, even.
Yeah, I completely agree with Jesper. apart from the business about dealing with us guys. But a key part of that collaboration early on is making sure that the validation exercises are done clearly and transparently to identify potential biases and to give everyone confidence in the outputs.
I agree with Ali, but I will add in the naivety I had in just saying, can we not put something on the turbines and not having engineers in the room? So we had the developers, but we didn't have the developers engineers. And I think, don't be naive, you really need to think through how you're going to attach, how heavy things are. Polly can tell you the hassle she had from every angle about that, but don't be naive. You need to start early in the planning and design of the turbine to be able to put the equipment on that will answer these questions.
I think this sort of key thing I keep thinking about, and it's sort of a thread that's been running through a few things that we've talked about so far in this conference, is data sharing and thinking about how you put the infrastructure in place so that it's really easy to make sure that this data that's getting collected at great expense is accessible and can be used, and then that data that can then be used to sort of inform the assessment process for the next projects. And how do we make sure that actually we're collecting data that gets used and is useful, rather than maybe a slightly more academic exercise, and just making sure that it really does have the use and value that we want it to.
Well, thank you, Angus. I think that are some nice last words, I think, for the panel. So thank you to all the panel members, and thank you all for joining this session. I hope it was interesting, you learned something from it. And give a big applause to the panel.